Okay, thanks for joining us for the Western Wheels Conference. A couple quick things before we begin. If you need a certificate, you'll find the link for that here. You'll need to submit a separate request for each session that you attend, and you should receive your certificate in email within 24 hours of submitting the request. If there are any handouts available, you'll find those there. And if you're interested in learning more about any of the products featured in our sessions, that'll take you to the product page for each one. And if you click request pricing, that'll add it to your wish list. Here we are at the wish list. You can either complete the form and submit it right away, or you can keep browsing around and adding items to it to get one big quote. And you can always get back to your wish list right up here in the top right-hand corner. That's it. I hope you enjoy the session, and we'll see you on the other side.
Hello, everyone. First of all, I want to thank you for taking time to attend this training presentation. And after that last year, what I call instructional disruption, I really can't imagine how hard that was on you and your students, and I really applaud your efforts. My name is Tim Dwyer, and just a real short background to kind of set up why we're going where we're going here in the next hour. I owned an import auto service in Tulsa, Oklahoma for about 25 years. Sold the business to pursue teaching. I was always, as a shop owner, I was always in need of good technicians, and finally decided that needed to grow my own maybe, or teaching interested students might be a rewarding way to help our industry and really get back to an industry that was good to me. So, however, I way underestimated the degree of difficulty of teaching, and as a result, I have a deeper respect for those of you that have been doing it for a long time, especially in teaching high school. So I stuck with it for about 12 years before taking this job at ConsuLab, and I tell you that today because this presentation is going to be a little bit more of a how to teach than what to teach. It's not so much about engine performance as about student engagement. And I feel like here at ConsuLab I can help other instructors with some of the struggles that I had getting that student engagement. So the title of this is Engine Performance, a Campfire Teaching Technique. The main, call it a life preserver, that was thrown to me when I was struggling at about year 3 of teaching. There was multiple problems I was having, but the student engagement part was the part that really bothered me. I found a strategy called team-based learning, and I could ramble on for hours about that. That's not what we're here to do today. If interested, we could do a class on that too. It's a lot of fun. It's probably more fun in person than it is virtually. But my big takeaway from doing team-based for about 9 years was that corporately the class was smarter than the individual, and meaning that students started out as a group, they evolved into teams, which is good because it means they're working together and communicating. But the team was always smarter than any individual on the group. And so when I say a campfire teaching technique, we're going to kind of do that today. And of course this is virtual and even not even live. I mean, we pre-recorded this so that you guys can watch it at your discretion or in your time frame. So I'm going to explain a little bit more about how it would work in reality, and hopefully you can take it back and apply it in your classroom. Maybe you're already doing it in your classroom. But long story short is we're going to kind of gather around a campfire and discuss the problem being a check engine light. And we need to listen to everyone's thoughts. Everyone gains knowledge and experience from the other people at the campfire, so to speak. And it's a real valuable way to get everybody engaged. I would want in our class, if this was live, I would want everyone to contribute. And when I was teaching, it might be that I came in the morning and we got class going, and I had a repair order and the key in a car with an issue in it, and I would hand the key and the repair order to a particular student, and we'd go out and all gather around in a circle, and it was up to that student to diagnose the car. I'd say, this is the car that's in your bay the first thing in the morning, and it's your responsibility to diagnose it. They'd read the repair order and proceed to to perform their strategy, which really as a new learner they don't have a strategy, and that's what hopefully this is to help them develop. But I would urge the rest of the campfire attendees to just remain quiet and let him go, and let's see what he does. I, on the other hand, as an instructor, would reserve the right to question everything he did, because I'm kind of curious what his thought process is. So it would be, they might put the key in the car or in the ignition, and start the car, and I'd say, what are you looking for, listening for, why did you do that first? And you would hear his thought process, or everyone in the campfire would hear his thought process. And eventually they might run out of ideas. And I would allow them to, what I call phone a friend, where they might ask somebody else at the campfire, what would you do, or what did I do wrong, or, is this right? Is this particular test right or not? And then so slowly you start getting more engagement. Eventually it kind of opens up to where I'm letting, in a controlled fashion, but I want everybody to contribute and understand why we're going this direction. Why are we performing this test? What is the expectation that we're looking for out of performing this test? So it worked pretty well. It's hard to control sometimes on a training vehicle, because it's a car with a hood up. I'm going to show you what we're going to do today, and without trying to sound like a commercial, I think our engine benches work really well for this particular application, because you can gather around it. But and being a let me just go ahead and introduce the patient to you here, so to speak. And I say that to the technicians I had working for me too. I'd say, you need to know the car you're working on before you can fix it. You need to know what the systems are, how they operate, how their strategies are, what their logic is, how to read their wiring diagrams, how to understand their service information. And when when I hand you the keys, you're on. It's not to walk out to the car on your phone and get in and take off for a test drive without paying attention. I want you to be observant of everything. I want you to look at the keychain. There are 100 different keys and weights on that keychain. When you walk out to the car, is it sitting level? Is it what do the tires look like? Are they inflated correctly? Are they worn irregular? Are they all the same? Are they different? The obligatory walk around looking for, dents and dings that you're maybe getting blamed for later. But then when you get in the car, there's some processes too that I was pretty adamant about. As an instructor to my students, I wanted them to totally get and to get in that habit. That's part of their strategy. But, as a technician, I kind of urged my technicians to get this routine down too. So let's kind of begin. This is the patient. It's a 2014 Hyundai Accent, and this is what the patient looks like that we're going to be working on today. We've pretty much taken the engine and transmission out and put it onto a bench to where it starts and runs. We've got a DLC available to us. Actually, I'm going to let Nathan explain some of this. I've taken what I wanted to present today, and again, I'm in Oklahoma. The engine bench was up in Canada, where ConsuLab is. And I had an idea on how I wanted to walk through this presentation, so I wrote up a video storyboard and had Nathan, our Nathan Banky up there in Quebec City, do the video of what I would have done had the bench been in my hand. So here's a look at it. Again, 24 Hyundai Accent. I'll explain the console link as we go. It's got a G4FD engine in it, which is a 4-cylinder. GDI engine, and it has a manual transmission. So, like I said, got to get familiar with it. Otherwise, you don't really know. If you don't know the system, you don't know how to fix it. So I'm going to go to the next slide and let Nathan introduce this bench to us and do a walk around.
So let me introduce you to this ConsuLab product. It's an engine bench, very similar to ones that we've had in the past. However, there are a few differences. It's still got 4 wheels, it's still got an engine and a lot of the same features, but really the entire area here where the rubber meets the road, where the instructor, you or the student interacts with the product, is totally different, totally redesigned. So we no longer have a fault box underneath. We've still got the instrument cluster. We've got a redesigned breakout box. We've got now integrated data link connector breakout box. The data link connector is right up front and center. Ignition key. You got a special switch I'll talk about later right here. And now you've got this student learning platform. And we'll get into the details of that after. Now, down at the front, we've got the fuel system, gas pedal, we've got the battery. It's got an integrated battery charger so that you can leave it plugged in. A main battery cutoff switch with a spot to lock it with the padlock. So you can lock it out, tag it out. You still got the cooling system. Of course, this is a GDI engine. Lots and lots of access around the front of the engine here. Around this side, you can see we've got the exhaust, ignition coils, all that jazz is there. Everything's nice and easy access. We've got the fuse boxes right next to each other, and you can see the evap system down there. So that gives you a pretty decent overview of the engine bench.
And this is what I would do with my students too. I would walk them around and make sure they understand. Actually, the exercises that come with this engine bench, walk them through just the basic engine ID, and then this specific engine ID, and then component locations and sensors and actuators, and then some wiring diagram exercises before they even get to a point where they can look at an issue with it. So that's kind of where we're going to go today. So I think it's important. I assumed an awful lot when I was first starting teaching that students had the experience library I have as far as sounds and noises and smells and feels and whatever. And I think it's worth taking a few minutes to make sure everyone understands what a known good engine starts and sounds like. So it's at this point in time I would do just that. I'd start up and let them kind of listen to it.
And we'll just see what it's like, known good. Coming up to temp. It's running beautifully. Runs perfectly.
So part of what I would I guess recommend students are, again, it's back to that being observant thing, is when you first sit down in the car and put the key in and you turn the key on but you don't start it, you should do a mental check of the bulbs that are illuminated on the dashboard, meaning most cars go through a bulb check session where they kind of make sure that the bulb is working, and maybe the system is running through a self-test system and illuminating a light bulb. But you want to look and see what's on, make sure you do have a check engine light that will come on and hopefully go off. You have an oil light, maybe an alternator light, and then of course in this particular case this engine bench is not an entire vehicle, so there's modules that are missing that will leave a light on the dash on these trainers here, like ABS and traction control and airbags and things like that. So I want to familiarize the students with that to make sure that they know they're oriented where the lights are and the ones that are going to be affected by engine performance in particular, and then of course the check engine light itself. So again, like I said, there's lights on this that are not part of, that don't have modules, and they will remain on. The main one I'm looking for is that light right there, and I want the students to understand where it's at, and we're going to be watching for that in our diagnosis here. So now, again, I haven't inserted any kind of a fault into this engine. I think this particular walk to run scenario is best to, like we did known good. I wanted them to hear that. I want them to look at all the dash lights working correctly, and now I want to prove that we have scan tool communication on a known good engine. So let's do that real quick. I'm going to have Nathan do that, and then we'll...
All right, so let's go through hooking the scan tool up to the engine trainer. I'm going to take the dongle, plug it into the DLC. We'll see right off the bat, as soon as we turn the key on, we've got communication going on there. We can see that through the DLC breakout box. We're going to go in quickly. We're going to go automatic selection. We've pulled up the VIN. We're good to go. We're going to go in with a North American car. And we'll do two things. We'll pull up live data, and then we'll take a look at the codes. So we're going to go into Diagnose, Control Unit, pull up the engine control unit. pull up some live data. And we're in. So we've got live data, all the different values. We can see the coolant temp, we can see the target idle, we can see system voltage, everything else. Once we fire this up, we can get all kinds of live data out of there. We can also get trouble codes. So let's see if there's any codes in the system, see if the last guy, hey, look at that, the last guy did his job. We're all clear, good to go.
Okay, now we know that we can talk to the car, and the students have a better idea. I guess I want to make sure everybody's up to speed on how to hook a scan tool up and things like that. Again, I don't want to assume anything. So next is, handing a repair order to someone with the customer concern. In this particular case, it's the engine has died, or it did die, and it restarted, but upon restart it has an extended crank. So I would stop and ask, perhaps the student with the key, or again the team if I need to, what's the first thing we're going to do? And my hope is that they answer verify customer concern. So let's do that real quick and see how that sounds. So I'm stepping forward a little bit. I've got I'm going to call it a case study. I don't call them bugs or faults anymore. I like calling them a case study. I have the case study inserted, and this is what they're going to hear. And so unlike, bug hunting or fault hunting or whatever, I don't think there's anything wrong with going back and forth and the student seeing you actually put the fault in there, or the case study in there, and take it back out so that you can demonstrate before and after, or known good and fail. With this particular bench, you're going to see how we do that, and it's not anything that it doesn't give any secrets away to the students, so to speak, but it's really great for an instructor-led type of a lesson where you can kind of go back and forth, So now we just for fun showed them what the customer complaint was, okay? But I want to actually, I'm going to stop here and show you guys how we made that concern happen.
All right, so I'm going to fire up the engine, and then I'm going to insert case study 02, and we're going to see what happens. So I fired up the engine. We got no check engine light. It's running beautifully. We're going to go in the student menu. We go to case studies, case study 02, check engine light on, extended crank. We're going to press start the case study. Boom. It stalls. What just happened? We don't know. Okay. So now let's try and crank it. See what happens. That's an extended crank. So if we look over here, do we have a check engine light? We got no check engine light.
So at this point, I'd stop and ask the students, I thought the customer complained of a check engine light. Why don't we have a check engine light? And we would go through the strategies involved in engine performance, or basically, not necessarily just Hyundai by any means, but how manufacturers sometimes will require a couple key cycles before it will turn the light on. So I call it a drop anchor here, so to speak, and we discuss it and make sure everyone's clear, as to why the check engine light isn't on and it's going to come on.
Okay. Let's do a second ignition cycle. So we'll shut her down. We've still got the same problem. It'll be another extended crank. We'll see what happens. Now what happened this time? This time we've got a check engine light. So we probably have a clue, probably have a code, and that could lead us down a path.
So this is where, again, we would stop and corporately discuss what's the next step. And you'll hear a variety of things. Of course, we got the standard parts store answer of hook a scan tool up and find out, what the code is and replace that part. And that's all fine, good discussion. They need to learn it in your classroom instead of out there on a customer's car. But so I listen and we make a decision, and for the most part, I've told Nathan what I think is going to be the next step, and this is where we're going to go.
So now let's go in, grab the scan tool, and pull the codes. See what we get. So we've still got the case study in. Fire up the engine, come out of here, we'll go trouble codes. Boom, we've got a P0335 crankshaft position sensor A circuit code. It's active. So now your students can go through using whatever service information you've got and diagnose and find that problem.
So my question is just this: after they find the code, they need to understand what is called the enabling criteria. They need to understand why the computer would turn that light on and have that code. So this is where we force them back into service information. We probably step away from the engine bench, go to the computer, look things up. I think they need to learn how to do this. I think it's very important that they understand how to read this information, because they think it's all, right there, that it says crankshaft position sensor. Let's put a crank position sensor on there. Well, why? Why do you say that? And are you willing? I used to ask my technicians, are you willing to base your paycheck on that? Meaning, if you're wrong, are you going to give me the money back? So we go to service information. I generally don't like to read off of a slide here, but I think it's important as a group here for us to understand what service information says about a crank position sensor, because it gives a little bit of a definition of the part. And again, I don't want to assume everyone standing there knows how this thing works. I think when your class is ready to diagnose a case study like this, you've probably gone through most of an engine sensors and actuators and how an engine mechanically works, etc. But you don't know that everyone's got it, so let's stop and take a minute and refresh our memory on what a crank position sensor is. And it's a magnetic type sensor that generates voltage using a sensor and a target wheel mounted on the crankshaft. There's 58 slots in the target wheel, where one is longer than the others. When the slot and the wheel aligns with the sensor voltage outputs low. When the tooth and the wheel align with the sensor voltage outputs high. During one crank rotation, there are 58 rectangular signals and one longer one. The ECM calculates engine RPM by using the sensor's signal and controls the injection duration and ignition timing. That's important for the students to know. So using the signal differences caused by the longer and the shorter slot is how the ECM identifies which cylinder is at top dead center. But what we're looking for is the criteria and why did it set, and it says right here, if that signal, that reference mark, isn't detected 2 or more times during starting, which is our second keystroke, the code is set. Doesn't mean that there's a bad sensor, it just means the computer has not seen a signal from the crank sensor. And it's important to make sure they understand it before you move on. Hopefully they say that and not you. It's very hard for me to stay out of being the one dispensing all the information, but I sure like bringing it out of them. So we might not move on until somebody makes this statement. Mitchell has some cool little charts that I think it's worth breaking down and looking at. They take the code and a single code and multiple codes and bring together the items that perhaps would match with that code. They're showing here on the P0335, it could be the crank position sensor, it could be the PCM itself, it could be the crankshaft, or it could be cam position sensor. And then again, if you have both the 335 and 336, it's probably either a cam or a crank sensor. And it's probably due to a correlation situation. I like the little chart on the right there. It talks about the silver bullets, basically. The number of repairs for that code have been, pretty heavy toward the sensor itself. 309 cases have been repaired with putting a sensor on there. However, 4 of them have had a control module put on there, and, as we say in the industry, it needed that anyway, right? 2 have had a cam position sensor replaced to fix this problem. And then 2 actually had to have a crankshaft put in there, which sounds pretty catastrophic, but nonetheless, it's been documented. At this point, I've been dwelling and pushing or beating this into them about being observant. I'm asking them, is there anything else that we notice other than the check engine light and the extended crank that's happened with this particular case study? And I wait and wait, and the hope is that they're going to come up with the answer. If this was live, I'd stop and wait for the chat window to light, I guess, blow up and see what you guys came up with too. But I'm going to kind of walk you on through again what the service information says, the symptoms perhaps that go along with that particular code. And start off with engine stalls, which we saw it did. When Nathan inserted the fault, it did stall. Engine does not start. In this case, it does. Engine starts hard. We have that problem. It runs rough. No, can't say that it does. Engine stalls at idle. No, it hasn't, other than after we inserted the case study. Didn't notice the oil pressure light on. Can't really tell if it hesitates or has lack of power, because again, it's an engine bench and we haven't test drove it. Engine stalls and does not restart. No, not having that problem. Tachometer inoperative. I think we have that problem. And my hope was that before we got to that part of this slide, that one of the students, if not more, have already made that observation. So
here
let's look at that.
We've got the scan tool set up. We're watching the engine speed. We can see it. Speed changes. It essentially is the same as the tachometer over here on the instrument cluster. And if I put in the case study and we fire it up, it's going to be a long crank. We still have engine speed. Now we have engine speed on the scan tool, but what do we have over here at the instrument cluster? So one of these two is a little bit smarter than the other one. Still getting a speed.
So another good place to drop anchor and ask for discussion. How does the scan tool see engine speed if the crank sensor is not producing a signal? And we're going to hope that they come up with the cam sensor. It's going to the cam sensor, looking at it and allowing the engine to start up. Otherwise, we probably would have a engine died and no start. So all good information, and we're working our way down to the real problem. But in reality, I say we've simulated customer concern. We've noticed the tach doesn't work. We noticed check engine light on. We've looked up the code. We kind of understand why the code's on. Where do we really start? I mean, again, like I said, the parts store parts scanner would be throw a sensor on it, but that doesn't necessarily mean it's going to fix anything. I think it's important to teach your students to not disturb anything, to try and catch the culprit in its native state, if you can. And so I want to kind of push them in that direction. But I had this benchmark that I pushed to my employees as well as my students, that before we even start any type of a electronic or electrical or a no code drivability problem, or even a code drivability problem, we start with the battery. And I think it's important that they understand that why you need to have a functioning, battery at rest, cranking voltage, and charging voltage before you can really start diagnosing anything. Otherwise, you will be chasing your tail. So let's check, or let's have Nathan check the battery for us.
All right, so let's check system voltage and also see what the charging voltage is at with the engine running. So we've got a couple options. First, we'll turn the multimeter DC volts. We'll set it down here. We'll go down to the battery, and we've got 12.7 volts. And if we come up to the DLC, we've got 12.7 volts. If we fire it up, we can see the voltage drop while cranking. Now it's running, voltage is coming up. And we're up to right around 14 volts. Beautiful.
So each time that they do this, those numbers start slowly getting etched into their brain. They start realizing that a battery at rest is 12.6. That state of charge, they realize that it shouldn't probably drop below 10 during cranking, and then once the engine starts up and the alternator starts taking over, that we should probably have at least 2 volts over rest voltage, and that's all good. I might have even stopped the students and ask them what we're going to expect when it starts up before I started it, and see, what kind of discussion we have there. So, okay. Now we know that we have the patient's healthy enough for us to start working on. It's got good blood pressure and all the vitals are good. Now we can start looking for this crank sensor, and got to kind of know where it's at. So maybe I'd send them to service information and let them look up what it even looks like, and perhaps the location of it. So here's the beast. It's a not a separate sensor without a pigtail. This has actually a pigtail on it, so that tells me a little bit. This picture that's in the service information shows it located there, and I know enough to it's pretty drilled down or focused picture, but I know that's not the front of the crankshaft. Looks like a bell housing to me, so I'm going to assume that the crank position sensor fits in on the flywheel end of the engine. So start looking there, and then I'm going to have Nathan actually go and find it so the students know where it's at. So now we know where the part is. And it might even be worth noticing, how many wires go to it, et cetera, et cetera. So, okay. So next step is kind of have to know a little bit about, I guess, how we're going to test. Meaning, like I said, I wanted to not disturb it, so there's some tests I want to do with in trying to catch it in its native form. We run into as we design these engine benches, and you probably experienced a lot on training vehicles that you use, or students' cars, or whatever you work on there, live vehicles, that automotive connectors were, I think, never designed to be plugged in or unplugged and plugged in very many times at all during their life. And in a training situation, it happens a whole lot more in the first period or second period of your day. So, we've incorporated a breakout box on our trainers, and the factory service information, when you pull up crank sensor, shows this particular circuit, so it takes some of the distraction away for a student. It shows that an automatic and a manual transmission harness connector, and that's basically one of the plugins at the computer itself. Make the students understand in this case, the Hyundai nomenclature, which they call that side of the computer EGGM-KG, and this is a manual transmission, so the MT, next to it denotes that. So what's going on here is when you unplug that, or not even so much that one, the wires that they go to this plug-in, that go into the computer, are numbered a certain way, and on our bench we've got the breakout box, which is directly, it's hardwired into the harness going to the computer, so the students really don't ever need to do any kind of back probing at the computer. I think it's a dangerous practice for a novice. You start getting naked T-pins touching each other at a computer, and you've turned this into a paperweight, and you don't really want to do that. So we brought everything up to a breakout box, and it's got the same labels that Hyundai uses, and all the pin numbers match service information exactly. So there may be some pin numbers that are missing because in the harness itself those wires are missing too. So this is strictly doing all your testing here is exactly like, in all honesty, back probing the computer. So everything the computer sees is coming through here. Fair enough? So now they understand, and it's pretty safe. We've even got the DLC connector over there with a breakout box, so they can do their testing there too. How you start probing around on a DLC, and next thing you know, you've got poor connections. You've got spread terminals and repairs to be made by you after hours, so that the next class can get a good situation, or a good, I guess, patient, if we're going to stick with that. On this tablet that we provide, this ConsuLink tablet, we've got factory wiring diagrams on there. They're available in student-friendly fashion, meaning they're just like their iPhone. They're in color. You can pinch and zoom on them. You can scroll back and forth. So we can pull up this particular circuit. The red circle shows again the Hyundai designation, the EGGM-KG, and it's showing a 2-wire crank sensor with the brown wire being the signal and the white wire going over to pin 67, and it's the ground wire. So now they kind of see a road map of where they're going. They know where the component's located. Let's kind of review, and before we move any further, what do we really know for sure? Well, we know the engine starts and runs. We know it has an extended cranking time. However, the scan tool does communicate, giving us a lot of good information right there. Check engine lights on. We have a P0335 crank position sensor, and we do know what the enabling criteria for that code is. We notice the tach doesn't work, but the ECM does see a speed signal from the engine, and now we know where the crank position sensor is located. So I've done this class remotely before with a live audience, and we take it from here in the chat room. The next step, I list where do you want to go? And I ask my attendees, you tell me, and I'll advance to that slide, and I've got these particular tests and measurements already pre-recorded, compliments of Nathan, and we can go from there. In the campfire with your students, I'd let them do it too. I mean, I'd say, here's a series of tests, or maybe let them come up with a series of tests and then say which one you want to do first. In this particular situation where this is a recording, I'm going to go down from the top to the bottom and show you all that we've done, but and explain all the nuggets of information and learning that come with taking that particular tack. So start off with measuring voltage, and we'll look at DC voltage first.
So we've already inserted the case study. We fired it up, had an extended crank. We did that twice. We got a code, we got a clue. So we got a P0335 crank sensor code. And right here from the case study, we can get into wiring diagrams, breakup box. We can just get some information here. Again, your students can go through the diagnostic procedures in whatever service information you give them. We'll go to the crank sensor here. So we've got a brown wire. That's the crank sensor signal, pin 89. We've got a white wire, crank sensor ground, pin 67. Let's just quickly see what we got there for voltages. So I'm going to grab my multimeter. Just going to put one of them on ground. Again, we got ground at the DLC, and we can make sure that ground works because we've still got system voltage, so we know our ground is good. If we go to pin 89, we turn the key on, we got 2.5 volts. If we go to pin 67, we got 2.5 volts also. Is that okay? I don't know. It's up for your students to figure it out.
So when you drop anchor here and have a discussion, it is pretty interesting. I go back to first thing as to why were you measuring DC volts? What were you expecting? And most of the time their answers will be the 12.6 or maybe the charging voltage if the engine's running, or the 5 volt reference, but 2.5 volts kind of throws them off, and there's a rich discussion about computer test bias voltage that you can land here and talk about for quite a while. The fact that it's on both wires, is an interesting concept for them, but I would make sure that they really understand that, that's what the computer's doing. It's basically running a 2.5 volt test voltage to and through the circuit, to and through the sensor and back to kind of determine integrity. So now then there's this.
So with the key on, we've got 2.5 volts at the signal pin 89 for the crank sensor. Turn the key off, we just leave it. We still got 2.5 volts. Why? And is that ever going to go away, or is it just going to sit there and kill the battery? I presume it's going to go away. Something just happened. Now we're down to 0 volts. So we can ask the students why, ask ourselves why. Why did we still have voltage even when the key was off?
So maybe even on the last slide, why is there voltage without the engine running? If it's a sensor that determines speed and position, and then B, why is the voltage stay on after the key's off? And they've heard of, or you perhaps already discussed the computer awake and asleep and things like that. I think it's a pretty powerful visual to actually be connected to that breakout box and watch the computer hold the 2.5 volts on there until a certain period of time, and then it turns it off and I guess goes to sleep, if you want to call it. So another good discussion to have at this point in time, and while I'm doing this presentation in about an hour, I think you should camp out and take some time with some of these things and not necessarily be in a rush. Make sure everybody understands. So let's measure some AC voltage, because if we know what a 2-wire crank sensor is, we understand what we're really supposed to be looking for. Nathan?
Now I'm going to do a different test. We're now hooking up both of our meter leads to the 2 different wires for that crank sensor. Now that's a 2-wire crank sensor. And if we look at the schematic, you can see it's an inductive type crank sensor. Old school style. There's 2 wires, it's going to put out an AC voltage. So if it's working all right, we should be able to turn the multimeter, AC volts, crank it over, and get some voltage. Now we're just getting a little bit of transient, a little bit of random voltage there. If we take the case study out, and we go back to a known good part, and we fire this up, we're getting 7 volts, 6 volts AC, and of course, it started right up. Now that's going to depend on engine speed. Depending on the engine speed, we'll get higher voltage. If we go back and put the case study back in, we're back to essentially 0 volts, or very close. We're getting a couple millivolts through there.
So hopefully that the visual will cement this particular situation into your students' minds, the AC voltage. Hopefully you've covered sensors and things by the time you get to this point of diagnostics, but to actually see it happen and be able to flip back and forth, I think is pretty powerful for learning. So we've done DC and AC voltage. We're down to the hunting and the killing right now, looking for the culprit. We kind of we know that we're getting an AC signal or AC voltage signal with the case study removed. You and I know as instructors that you didn't, or Nathan in this case did not reach around and replace the sensor while we were doing this. So for the most part, the sensor, we can't make it good and bad. We can intercept its signal and tell the computer something different. But for the most part, that sensor has to be good. So hopefully the students are kind of kicking that particular component out of their thought process, or maybe they're thinking that the plug-in at the sensor itself could be the problem, which is all good. So these are discussions you want to know before you take them any further. But we're getting ready to disturb the crime scene, and I want to make sure that they understand what direction to go, or I want to hear what direction they recommend before we go there. So. Got to know the specs. Back to this same wiring diagram, we looked up the actual ohm reading for that sensor, and it would be 774 ohms to 946 at 68 degrees. It's worth mentioning the temperature affects this test, and we're going to see that here in just a little bit. So these are things that they need to start parking in their experience library, because when they're doing this on their own, they need to understand the details. It's all about the details. So let's see where Nathan goes with circuit resistance.
So let's say that I want to test and measure the resistance of the crank sensor. I got a couple options. So I'm going to take my multimeter, put it on ohms. I can get in here, disconnect the crank sensor, get into those pins and measure it there. And your students can still do that. But we know that students, especially when they're still learning, can cause damage to connectors when they're disconnecting, reconnecting. So there's another way on this trainer, because we've got the breakout box. So we can go to the pins 89 and 67, we can measure the ohms of the crankshaft position sensor. Now, in order to measure this properly, we're going to have to go around and disconnect the engine control unit. So let me do that.
So this would be like probing it at the computer itself.
Depress the tab, connect the other connector. Now we don't have to go in and back probe at the ECM connector because we've got the breakout box, and the breakout box is permanently connected to the engine harness. So we can see we've got over limit, so we've got infinite ohms. If we turn the case study off, we get 960 ohms, 0.96 kilo ohms, which is dead right in the spec. If we turn the case study back on, we've got infinite again.
So I think it's important to know, for them to know, obviously, the old rule of if you're going to be testing resistance, you have to isolate the circuit. That particular harness on the computer is somewhat user-friendly with the lock pads and everything. Don't want them really sticking any kind of probes into the harness with it unplugged. That's why the breakout box is there. But also, they're getting a real-world way to isolate the actual circuit itself. I think seeing that well, I guess the spec did say 946, he got 960, but then we have a little difference in temperature change. I mean, temperature because of the engine's hot and all that. So all those are things that I think are worth talking about, because I think sometimes students take things real literal. If it's supposed to be 946 ohms and it's 960, it's a bad part. And that doesn't, you and I know that those are not far enough off to really, pull the trigger and change the part just yet. They're to be considered, and they're information that I gather in kind of two hands as I'm working on something. One is, totally fine. I'm not even going to think about it again. One of them is I'm going to keep it in the back of my mind, but I'm not derailing my process just yet because it's not a big enough deficit for me to get off this diagnostic train yet. We're not there yet. So 946, 960, good lesson to be learned. And again, just to review the specs on this 946 at 68 degrees Fahrenheit. I'm sure it's hotter than that on that engine right now. So they should be able to explain to you what are we left with. We have, technically the harness unplugged, so we have a wire leaving the computer, let's say it's the brown wire leaving and going to the sensor, through the sensor, and back through the white wire to the harness itself, which we have unplugged. So you've got really three pieces of this circuit left until we found the culprit. One of them, like I said, if they were really sharp, they know that when we remove the case study that we're getting an AC signal generation. So the crank sensor itself has to be working. So now we're down to, the wire to or the wire from the sensor. And let's see where Nathan goes.
So let's say that your students have isolated it. They know there's a problem in the wiring. They've tested the sensor. It's got a good resistance value. Everything's good. And we want them to find out exactly which part of the circuit has got a problem. Well, they can do that. They can use multimeter. Here, we'll put it on a beep since I won't be able to see it. And so we check here. Meter's still good. We'll put this up high so you guys can see. So we'll put that there. We'll go down to 89, which if you remember earlier, is our brown wire. Okay. So if I go from the brown wire here on pin 89 and I come over to the harness side.
Nice one-handed unplug.
At that pigtail, and I go to the brown wire, I got nothing. If I come to the white wire, which we said was pin 67, and I go to the white wire here, what do we got? Beautiful. And now, if I turn off that case study, and I come back to the brown wire, and we check it once more, we're going to see that wire is now fixed. So we've just found the problem, validated the problem, and now we've fixed the problem.
There's a lot of satisfaction and a lot of confidence that's built from actually finding the problem, in my opinion. I know when I was teaching, and again we had not the best stock of training vehicles. We did not do live work. I never really liked that idea. I know a lot of you do that, but I never wanted to get involved in that. I ran a shop too many years to want to run it with students. But having said that, training vehicle, I had a really hard time consistently replicating a problem like this. It seemed like the first couple students I sent out, if I put a fault into a car, got a somewhat clean experience, a pretty pure experience, but they disturbed things in doing what they're doing. And then the second group or third group, by the time you get to the fourth group of guys going out there, they're totally lost because things were left unplugged, things were disturbed, things were broken that weren't broken in the first place. And so I like the idea of having a repeatable, consistent way to put a case study into a vehicle's engine and build confidence. And so we've got to the point now where they could technically go to the parts counter, and I used to tell my students this too, that I want you to be the guy at the shop that walks to the parts counter and says, I need one of these parts, not let me try one of these parts. There's a lot of parts changers out there, and I wanted my students to be guys that had looked at a particular problem from multiple angles and were confident that they either needed more time to go in this direction or they found the culprit. So I think this is a great teaching method and definitely a cool tool to use to get build student confidence. So one of the options, of where do we go would be checking waveforms. Not sure how many of you are using oscilloscopes, but I want to show you how that plays out here too, because that might have been the first choice of some students that are a little bit more experienced. Quick look at service information on how to hook up. It's always worth having the students know that before they go anywhere. And then let me see what Nathan comes up with.
All right, so let's pull a quick oscilloscope pattern from the crank sensor. So I've got the scope. We're going to go into 89 for the signal. Sorry, we'll go to ground here. And we'll go to 89 for the signal. And let's fire it up. And give me a second and I'll set up the trigger. So now I've got the trigger set up. We got a beautiful view of that pattern. If I bring the speed up, we can see our frequency changes and the amplitude changes. Of course, we're getting over our trigger point. That's normal. If I bring the trigger up just a little bit more, there we can see different changes in the frequency and the amplitude as I give the engine a little bit more speed.
So, love using oscilloscopes. I like those little U scopes. They're just a one channel. I call them, they're great for triage, for going out and just kind of doing a real quick scope pattern on something. Hopefully you're teaching oscilloscopes, maybe not at the high school level, but definitely at the post-secondary level. Back to service information and known good. These are things that they need to start etching into their brain, what a 2-wire sensor looks like, a known good one. And then just for fun, just to kind of wrap it up, let me show you what it looked like with the case study inserted. Your basic flat line. So, when we do these presentations, it's easy, to seem like we're just showing off our equipment. In all honesty, when we've been reduced to doing things from a distance or even virtual or, like we're doing right now with the video, I have to use the tools that I have. And this was kind of fun to be able to have Nathan be my hands up there in Canada, because I didn't have my hands on a bench, and I sure don't have one in front of you all. If after this type of I call it a rich discussion, you want to continue to imprint on their brain, how a crank sensor works or how some of the engine performance sensors work. We have another kit that looks kind of like our Ohm's Law trainer, except it's called the MD4000, and really I like it in the fact that all those little components are actually parked in there right now for storage, but you can take all of them out except for the power supply and isolate and just put back in the component that you're wanting to talk about and teach. For an ADD instructor, and for students with ADD and Asperger's and things like that, sometimes seeing all that at once and trying to focus on just what you're trying to teach them is a little distracting. You can really hone in on just the particular component. So let me show you real quick what the crank sensor looks like. It's on a clear plexiglass panel. We call them moduponents, and this one in particular has a, the kit itself has a 12-volt power supply that you would plug into that dial at the bottom for the RPM. So we have an electric motor that spins the tone wheel up, and then the sensors mounted there that you can connect your DVOM, or your oscilloscope to, and recreate patterns and change RPM and watch the pattern change too. So you can kind of focus a lot more on just the sensor. They see it in their hands, they see it spinning, they see the tone wheel, they understand the air gap, and all that. And it just kind of reinforces the hunt and the kill that we just did on the engine bench. Provided with this particular kit, we've got wiring diagrams so where you can have the students, you hand them, I'll show you the worksheet here in a second, but you hand them the worksheet and they create the wiring diagram and do the testing. This is a very visual part. Some people like reading instructions, and so I've got it written to where you can go through and step by step, tells you where to hook the red wire, the black wire, and yada yada, and what you set your DVOM on, and then the bottom part is to be filled in with measurements that they take. So that works on reinforcing, their understanding of a two-wire crank sensor. And just while we're here, I'll show you we've got MR sensors that take a 5-volt reference. We've got a Hall effect sensor, and all of them, you can put a scope on them all and illustrate waveforms. We've got a map sensor that you can use and actually apply vacuum through a little syringe that we provide and watch the reference, the signal voltage change. TP sensor, you can do a sweep of a throttle position sensor on a scope or even a DVOM and show the difference. So all that kind of brings us up to, where if this was live, I'd ask you what questions. I'm going to fire you at probably Jake in this particular case. If you have questions that he would be more than happy to take them up, I'll give you his email here at the very end if he hasn't already given it to you. But I want to show you one thing real quick too. We've been last hour working with the Hyundai engine bench, and part of what I really enjoy about working with ConsuLab, and it feels like an evolution of a tech to a shop owner to a teacher to helping write curriculum and do training for to help teachers, is the attitude and the culture, I guess I would call it, at ConsuLab, and how they develop products. So back in, we as the education team, we traveled up to Quebec City, before pre-COVID, we were going probably 3-4 times a year and having these brainstorming sessions. Back in, I think it's February of 2019, we were up in Quebec City, which, yeah, it was cold. Here we are walking to dinner in downtown Quebec City, and I will admit I was the one that went down on my butt in the ice. But at the shop, in the design engineering part of ConsuLab, the birth of another engine bench was happening, and we had met really probably before that up in Quebec and had these brainstorming sessions where we talked about if you could think big, what would be the next engine bench that we would design, what would it incorporate, and that's somewhat how the ConsuLink, that tablet-based thing came to fruition. But the engine bench itself that we most wanted was, we wanted certain features, and it was GDI, we'd like turbo, we wanted possibly stop-start technology. And so when I was up there in 2019, this engine bench was in its really basic stage of engineering. It was a Cruise engine bench, Chevy Cruise, 1.4 liter turbo with GDI, a fuel system on it. And they had the frame, you can kind of see it up there. It's not the blue yet because it's just everything being roughed up. And the engine was sitting on the frame, mounted, and they were learning where to position things. And so it went through many changes until it became what it is today. I kind of joke, it looked like the wiring harness was thrown up on the floor around it, but basically they could get it to start and run that way, and we worked through it. here's Nathan again. There's Marty, one of the smartest fellers up there. The guy on the right, you can barely see Guillaume. He's our electronics guy. He's the one that does all the computer programming that fools the engine into thinking something's going wrong. But we took that particular cruise engine bench and made it into this. And so it's a 2019 through 2016 GM engine with stop-start technology and the ConsuLink tablet that we just went through and showed how we can insert case studies in it. It is the push button start, not to be confused with stop start. It does have the push button technology with the key fob, and we've got a little container there where it gets trapped so it doesn't wander off and render the bench useless, so to speak, or an expensive fix. It's probably, well, it is the first bench that we built that has two pedals, a brake and a gas pedal. Has an automatic transmission, and again, if we're going into automatic transmission and a brake pedal, then of course we have to have an axle coming off the transmission, a caliper, and a brake system to be able to stop it. But all these things had to be incorporated for us to really replicate a stop-start situation and be able to teach that and even diagnose failures in it. Part of the stop-start, you wouldn't believe the list of criteria that's involved in whether or not the stop-start is going to be engaged or not, and HVAC is a big player in it. So not only can you teach engine performance and things like that, you can teach heating and air on this particular engine bench too in the same footprint. And being a turbo, we thought it'd be kind of cool to throw a gauge on there, and then if we have a gauge, then without any way of power stalling it or testing the boost, then what are they going to get out of it? So it was soon realized that you can't step on the gas and the brake at the same time without falling down. So we put a little button on the dash where you hold it down and it actually engages the brakes, and then you can accelerate it, and students can watch the boost build up. And again, just a good visual. And of course, then we put the tablet on there too with that we are calling the ConsuLink, so all the case studies can be inserted and by the students. Really, the whole point of this was to kind of take the instructor out of it a little bit, where you hand the student a repair order style sheet and tell them to work on case study like we did today, O2, and they walk over and they're able to press on any of the blue buttons and have access to it and insert their own case study. And they have access to service information, how the bench operates, the breakout box, and things, wiring diagrams and things like that. I'm going to continue this video and show you I'm going to go to a live where I can bring up the tablet, and I'll show you how it navigates a little more here in just a second. So let me introduce you to our newest toy, the ConsuLink, which is the student learning platform, the tablet that I showed you on the Hyundai bench. This is actually programmed for the GM 1.4 engine trainer with AC and stop-start. Real quick tutorial. The top we're going to start with, of course, is safety. This is a touchpad. I have it mirrored to my computer, so I'm able to kind of work it just like I would if it was on an engine bench, even though you can see up here it says no connection to the product, so there's some things that I'm going to be limited on doing, but you got to see it in action in the presentation that you just saw. So always talk about safety first. We list all the safety features of it and component locations, etc. To navigate around, to go back to the main menu, you just hit home. All these blue buttons are on the student access side. So like I said earlier, you can give them a repair order and have them come up and navigate their own way through a particular case study. We've taken the operation manual for the product and put it here for the students to be able to learn how to use it and where all the components are. Taken a component ID and showed them where what all the features of it are, the ignition button, fuel tank, climate control, things like that. So at any point in time they have at their access their own reference library for the product itself. And we tried to keep this trapped on the pad so that there wasn't necessarily internet needed, because we know that a lot of campuses have a very proprietary about devices getting on their network. So this is just kind of a standalone deal. We've got two other things that I want to show you. The breakout box, which is this again is factory service information copied to where the students can look up the breakout box pin, which they're going to need this for a couple of the written exercises that they have to do before they get to actually work on a case study. But just like everything else that we've learned to know and love nowadays, you can pinch and zoom on it and scroll around. And so between that and the wiring diagrams, similar type of a deal, you can go look around for what you need. You can blow it up, and the resolution stays pretty good all the way through. So the students can bring up what they need right on demand, on touch. I want to show you the part that they'll be probably living in, which is the case studies. In the student accessible side, they've got on the GM bench, they've got access to 9 case studies that they can insert themselves. So let's say you told your student to go up and insert case study number 4. They would come over and walk and touch that button. This looks similar to what Nathan was showing you when we had him doing our case study 02. At the top, it'll tell the customer complaint or customer concern. It'll describe it a little bit further under problem here, where it says customer states engine is not running well, feels low on power, check engine light is on, please confirm and advise. The boilerplate statement is, clear our codes before you begin this case study. And that's because they're going to be inserting it, and we really want them to have a clean patient to work with. We obviously understand in the industry you wouldn't want to clear codes before you started working on a car, but this is a training session and a training situation, and we want to make sure that they're not chasing the last guy's case study. So before they do anything as far as inserting their own case study, they should clear all the codes. And then we just say that following manufacturer's troubleshooting procedures, you should be able to diagnose it. We do put in here a disclaimer that we think it's not recommended for them to disturb any electrical connectors. It's kind of up to you, obviously, as an instructor, how far you let them go and how much you're going to let them touch and unplug and plug in. But for the most part, it's written here that they're not really supposed to disturb it. They should probably come to you, like on that last case study, and say, we feel like it's between here and here, and we need to isolate. And then maybe you would unplug the computer harness, and then maybe you would unplug the crank sensor connector for them, just to kind of at least try and control the control damage anyway. They can hook up a scan tool and etc. So they just read these on everyone. Again, there's another quick link to the wiring diagrams or the breakout box right here from the case study. And once they're ready to go, they just hit the green button and it'll start the case study. So they've got, again, 9 of them that they can work through on their own. And then let me take you back. And so now on the front of the instrument panel, there's another key that we mentioned, that Nathan mentioned, and you can unlock the instructor side, or instructor mode we call it, or you can go to the top right corner up here and hit instructor mode, and it'll pull up a pin pad. You can use the key if you don't want them to see your pin code, but oops, I don't even know it. So once you insert your instructor code, and you can change that once you receive the bench, by the way, and make it your own, or if a student finds out what it is, you can go in and change it. The orange buttons are lit up, and you have access to a little bit more enhanced information for your benefit. The instructor guide is similar to the operation manual, but it does have a little bit of information in there that is privy to just the instructor. It talks a lot more about the strategies and things like that. You do have access to wiring diagrams with faults, and since this is a recording, I'm not going to open it up, because basically it shows you a wiring diagram and where all the faults are located, and we kind of want you to control that and not let it get out of, into the public viewing realm. So, but just know that as an instructor, when you're trying to help them, you have a cheat sheet here where you can actually find where we put the particular fault. then you have your case studies, and I'm going to open that up and show you. So the first 9, they're CSO 1 through 9. They're technically the 9 that the students have, but you've got answers included in it. So you can see right off the bat, you've got next to the case study, the CSO1, you've got the code, the engine code that it's going to produce. So let's open that one up. And then the definition in there is similar to what the student sees, but you get more information. In this case, it says you'll have a permanent misfire. Fuel trims will be affected. On the tablet, open wiring diagram for faults, just to show you where the fault is. And the stop-start system will not operate with this current DTC present. And then we go on to tell you exactly where it is. That it's a cylinder 4 injector control circuit. So you've got the answers and a lot more enhanced information. Another one, and look at it, and basically it says the case study, we opened the number 2 ignition coil ground circuit between pin 3 of that coil and the breakout box pin X265. So you've got everything you need to look smart in front of these guys and not have to make more work for yourself. So there's those 9 with more information, but then you've also got what I'm going to call instructor-led case studies, and it's similar to what we did in the presentation I just did, where you kind of guide them through it, and there's nothing wrong with that. You show them, you put it in there, and you can simulate things that will help, cement that type of an image into their head. They'll actually see what's going on. They'll be able to see the process. They'll see the results, the measurements, etc. So we have ECT, MAP sensor ones, we have oxygen sensor ones, MAF sensor, you've got an accelerator pedal position glitch, so you can put a scope on there and do a sweep and watch the bad spot. Got valve timing problems, and then some stop-start, obviously, scenarios. So over here on the left, you've got kind of a quick menu to get to those, but then on the right is just that. Now I want to show you something on the instructor side too. Let's go back to the student deal. Let me open, let's say, CSO 6. If you'll notice above, in the orange box above where it says no air conditioning, there's a term called scenario number, and it's 1130. You can go back to here, and if you'll notice in the student portal, you can open it up, and there's a tab for entering a scenario number. So students are kind of hip. They watch what's going on. You might give them case study 03, and they realize they've done it, and then their buddy does case study 03, and they pretty much understand case study 03 is going to be this solution, and then maybe you want to come back in a couple of weeks or in final exam or at capstone or something and try and reinforce whether they really learned the lesson. And if you gave them case study 03, there's a chance they could have notes on it or a memory and remember what it is. Each one of those case studies in the instructor deal has a scenario number, so it would be 1130. You would basically, instead of giving the student a case study 03, you'd give them a scenario number, and they'd go in here and enter 1130, and they don't know what that is. So they'd have to actually diagnose based on their aptitude instead of just their memory. So we kind of give you a sneaky way of going back and assigning the case study that they may have been working through, and you can kind of find out if they truly understand how to diagnose it. So that's a real quick rundown on the console link. We feel like it really gives you an advantage on doing repeatable, consistent case studies. It builds a lot of confidence in the students, and eventually there's on the instructor mode, there's this fault insertion side too, and it shows you really where all 14 of the faults are, and then the advanced faults, and it allows you to also customize your own if you want to create a case study from an active fault. So you can kind of make up your own too if you want to try, and so you've got pretty much infinite amount of stuff to do, and a really easy way to save it, and an easy way to protect it, and an easy way to monitor it. So this was part of a lot of thinking and going into what the education team at ConsuLab wanted. If we were still in front of the class, what would we want out of an engine bench? They said dream big. I feel like this was a big dream. And our engineering department really came through with putting this together in really less than 2 years, even with COVID happening, to the point where it's now available. So we've got this on the Hyundai, we've got this on the GM bench, and I think our next product or engine bench in our sites is going to be a diesel engine. So that's today's commercial. I'm going to flip over and do something here real quick. I think maybe. Thank you all for allowing us to help you teach technology. I hope you got something out of this session. I put my email and Jake's email down here for you to reach out if you want more information on either this particular teaching strategy, on this presentation, or perhaps the products that you saw in there. And again, don't like doing commercials, but I sure like our product and I sure like teaching, and I feel like these two go hand in hand. And I know that your students would benefit from it, and that's what this is all about. So again, thank you. Enjoy the rest of your conference, and we look forward to working with you all in the future. Thank you.
That concludes this session. Thanks a lot for watching. Now for a quick word from our sponsors.
So today I want to show you one of the most exciting developments that ConsuLab has made in the 50-year history. You know, we've always been so focused on the interaction of how the product fits with the teacher, with the student. And we know that our products are made for really taking the students faster to the vehicle. So we go from theory, however you're delivering it, and we're trying to get them to the car or to the truck as fast as possible. And for a long time now, we've been working on and thinking about ways that we can change the way that the student and the teacher interact with the product. Specifically relating to fault insertion and also to what we call scenarios. So when we're trying to demonstrate diagnostic scenarios. And the way this was done in the past was with a fault box. And that's how we've done things for decades. But today's different, because today I'm showing you a new feature on our products. It's called a student learning platform. And it's a touchscreen interface that lets your students and you as the instructor interact with the product in many new ways. So let me show you a little bit more about that. Here I'm going to dive into some of the details. So here we're looking at it from a student's perspective. So a student walks up to the bench, they've now got access to all kinds of great information. They can get into safety warnings. They can see important safety warnings about the bench, learn about the emergency stop, learn about the hot rotating components. They've got access to an operation manual. Got access to wiring schematics. So engine performance wiring schematics, they can pinch and zoom, get the wire colors, the pin numbers, all the information for the engine performance wiring diagrams. They can get information about the breakout box. So all of the pin identifications for the breakout box are all there. They can access some videos about the product. Scan tool usage, a little bit about engine benches. Well, we've got component locators, so we can see all the various components around the engine. And then we've got a couple new and exciting menus. So we've got these things called case studies. And this completely changes how the student interacts with the product. This is pure magic, because now, instead of you, the instructor, having to be over the student's shoulder, come over, play with a fault box, do something, you could simply say to your students, today I'd like you to do case study CS02. And what does that mean? Well, let's try it out. We'll fire up the engine. We're going to click on the case study. And it says, start the case study. What just happened? It says the problem, we've got a check engine light on, extended crank, clear the codes before beginning each case study. And this is your student that just created this problem live. You as the instructor, you don't even need to be right here. You could be 6 feet, 2 meters. You could be in the other room. And now the student can go through following the OEM diagnostic troubleshooting procedure, and they can find what the problem is. So we give them the effect, and they go and find the cause. Now, above and beyond all of the student interface, we also have an instructor interface. So if we look here, we've got all these menus that are locked out because we don't want the students to have access. So if you click on one of the locked out menus, you need the teacher pin. So if I enter the pin of 0000, boom, we're in. Now we've got access to all these other menus, instructor's guide, wiring diagram with faults. I'd love to show it to you, but then your students would see where all the faults are, the fault insertion, the case studies, and we've got more and more case studies for instructors. So you've got different lessons that have already been created. So we can go in and get coolant temp sensor lessons. We've got 4 different coolant temp sensor lessons on this engine. And we explain to you exactly what to do, what voltages are going to be changed. It's kind of like a preset recipe. Again, we've got dozens of lessons and case studies programmed in here for all kinds of different sensors, for the intake air temp, fuel tank pressure, map sensor, CVVT, APP sensor. The other awesome thing about this is that for the student case studies, where on the student side, you had very limited information. It told you just the effect. Well, if you go into that same case study with the instructor's version, so if we go in right here, it tells you the code number, it tells you which pin the students are going to measure, it tells you the details, the wire color, all of the information that you need for that case study is there. So it makes your life so much easier as an instructor. Now, we talked about those scenario numbers earlier. You can even create your own. So you can go in kind of old school, put in a fault, and then create a case study from it, enter your information, and it would be scenario number 6622. And you could save all of your information that you want and then create that yourself. So you could create a custom case study, and you could assign it both to the students or to the instructors. Now, what's even more exciting is we've got another way that the students can interface with the engine bench. Not only do we have all of these case studies where we explain the effect, we tell them it's got a check engine light, or it's got an extended crank, or it runs like crap. We tell them that and we give them instructions. But as an instructor, you can also assign them pretty much anything you want through what's now called a scenario number. So if we go here, we click on scenario number, and here, I'll just fire up the engine. I'll give you guys an example. Engine started running, no codes, runs beautifully. I can give my students the practical assignment today. I go, guys, today you're going to do 4001. What is a 4001? Could be a placebo. Could be a placeholder number that does nothing. Could be a number that does something very drastic. Let's see what it does, a 4001. 4001. I don't know what that was, but I can tell you, we can hear the difference, and we can smell the difference. So that means that you can assign your students without giving them any information about what the fault or the scenario that you're inserting is. You can assign that to your students with a random number, and they can go through and do their diagnostic. The ConsuLab student learning platform can really change the way you teach using an engine bench. It's going to change how your students learn. It's going to make it easier. It's going to save you time. It's going to save you setup and energy, and let your students explore much more autonomously on their own. So if you want to find out more about this product and the other ConsuLab products that are going to have this same student learning platform integrated into them, you can check us out at consulab.com, or you can follow us on Facebook, Twitter, or LinkedIn. Thanks for watching.